Hi all, welcome to the YouTube channel Phi. So, in this video, we will learn some basics of the binary number system. Now, we all are familiar with the decimal number system, and we are using it in our day-to-day life for counting, as well as for performing the various arithmetic operations. So, this decimal number system consists of 10 different digits starting from 0 to 9. On the other end, all the digital circuits and the system works on the binary number system. So, in the binary number system, there are two digits. That is 0 and 1. So, if we see any binary number, then it consists of only ones and zeros. For example, let's say, there is one binary number 1010. But if you see, then the same number also exists in the decimal number system, right? So, to distinguish the numbers of the different number systems, usually they are represented by their base, or the radix. For example, for the binary number system, the base is 2. Because it consists of only two digits. That is 0 and 1. On the other end, in the decimal number system, since there are 10 different digits, so the base, or the radix of the decimal number system is 10. So, if we represent this 1010 in the decimal, then this is how it should be represented. But typically in our day-to-day life, when we are performing any arithmetic operations, then we are not representing this decimal number by its base, right? Because in our day-to-day life, we are only using one number system. But whenever we are using multiple number systems at the same time, then it is necessary to distinguish between these number systems. So, in such case, the numbers of the different number systems can be represented by their base. Alright, so now let's see how to count in the binary number system. So, counting in the binary number system is similar to counting in the decimal number system. So, first of all, let's see how the counting in the decimal number system is carried out. And the same rules are also applicable for counting in the binary. Now, I am sure all of us are already aware about how to count in the decimal number system. But perhaps some of us may not be aware about the rules which we are following while counting in the decimal number system. So, in the decimal number system, while counting, we start with the smallest number. And in the rightmost column, we start incrementing that number by 1. So, while counting, if we just run out of digits, then reset that column to 0, and then increment the next column by 1. So, that is how we get the 10 after 9. So, once again, we will follow the same procedure. That means we will increment the rightmost column by 1. And while incrementing the rightmost column, all other remaining columns will be kept as it is. So, in the rightmost column, since it is 0, so the next number will be equal to 1. And in this way, we can go up to 19. So, after 19, once again, the rightmost column is run out of the digits. So, once again, we can reset this column and we will increment the next column by 1. That means the next number is 20. So, if we follow the same procedure, then we can reach up to 99. Now, at the 99, if you see, then the rightmost column is already run out of the digits. So, we will reset it to the 0. And if we move to the next column, then the next column is also run out of the digits. That means we will also reset it to the 0. And then we will increment the next column by 1. That means after 99, the next number will be 100. And once again, we can follow the same procedure to count further. So, that is how the counting in the decimal is carried out. And the same rule is also applicable for counting in the binary number system. So, once again in the binary number system, we will start with the smallest number. And we will start increment it by 1. But in the binary number system, since there are only two numbers, so immediately we will run out of the digits. So, once we run out of the digits, then we will reset that column to the 0, and we will increment the next column by 1. Therefore, the next number is 10. And once again, we will go to the first step, and increment the rightmost column by 1. And all other remaining columns will get carry forwarded as it is. That means the next number will be equal to 11. Now, if you see the rightmost column, then it is already run out of the digits. So, now we will reset it to the 0. And we will increment the next column. But if you see the next column, then it is also run out of the digits. So, we will also reset it to the 0, and we will increment the next column. And therefore in the binary number system, the next number is 100. So, after 100, once again, we will increment the rightmost column by 1. And all other remaining columns we get carry forwarded as it is. Now, after 101, if we see the rightmost column, then once again, we will run out of the digits. That means we will reset it to the 0. And we will increment the next column by 1. And all other remaining columns will be kept as it is. That means the next number will be equal to 110. Once again, we will increment the rightmost column by 1. Therefore, the next number will be equal to 111. So, now if you see, then all 3 columns are run out of the digits. That means we will reset them to 0, and we will increment the next column by 1. That means the next number will be equal to 1000. So, this is how the counting is done in the binary number system. And if we keep on counting, then these are the few following numbers in the binary number system. And here are the following decimal numbers starting from 0. So, now we can correlate the binary number with the corresponding decimal number. For example, 100 in the binary corresponds to 4 in the decimal number system. Similarly, this 1111 in the binary number system corresponds to 15 in the decimal number system. So, this is how we can correlate the binary number with the corresponding decimal number. But the question is, suppose if we do not have this correlation table, and if we want to convert some binary number into the decimal equivalent, then how we can do it. And that is exactly what we are going to learn next. That means if we have any binary number, then how we can convert it into the decimal equivalent number. So, this binary and the decimal number systems are positional weighted systems. For example, if we take any decimal number, then the actual value which is represented by this decimal number depends on the digits in that number as well as the position of these numbers. So, here the rightmost digit is the least significant digit, or the LSD. And the leftmost digit is the most significant digit. So, as we move from the least significant digit to the most significant digit, then the weight of each digit increases by the factor of 10. So, as you can see, this least significant digit has the weightage of 1. And the digit which is next to it has the weightage of 10. Similarly, as we move towards the left, then the weightage of each digit increases by the factor of 10. So, the actual value which is represented by this number is the summation of all these products. That is equal to 3000 plus 400 plus 50 plus 6. That is equal to 3456. Let's take one more example. So, here the number is 10,987. So, here this digit 7 will get multiplied by the factor of 1. While this 8 will get multiplied by the factor of 10. And likewise, as we move towards the left, then the weightage of each digit will increase by the factor of 10. So, the actual value is the summation of all these products. That is equal to 10,987. Now, if the number contains both integer and the fractional part, then for the fractional part, as we move towards the right from this decimal point, then the weightage of each digit reduces by the factor of 10. And before this decimal point, for this integer part, as we move towards the left, then the weightage of each digit increases by the factor of 10. And the actual value is the summation of all these products. Now, in the decimal number system, the base of the system is 10. And therefore, the weight of each digit is in the power of 10. So, suppose we have a base 3 number system, then in this ternary number system, the weight of each digit is in the power of 3. Likewise, in the binary number system, the weight of each digit is in the power of 2. So, in the binary number system, these binary digits 1 and 0 are also known as bits. So, this rightmost bit is known as the LSB, while the leftmost bit is known as the MSB. So, we move from the LSB to MSB, then the weight of each bit increases by the factor of 2. That means here, the weight of the LSB is equal to 1. And as we move towards the left from this LSB, then the weight of each bit increases by the factor of 2. For example, in the given binary number 1010, this 0 is LSB. So, it will get multiplied by the factor of 1. Then the next bit is 1. So, it will get multiplied by the factor of 2. Then after, the next bit is 0. So, it will get multiplied by the factor of 4. And then after, this MSB will get multiplied by the factor of 8. So, if we see the decimal equivalent of the given binary number, then it is the summation of all these products. That is equal to 8 plus 0 plus 2 plus 0. That is equal to 10. That means the decimal equivalent of the binary number 1010 is equal to 10. So, let's take one more example. So, now we have 8-bit number. So, in this case, the least significant bit is equal to 0. So, it will get multiplied by the factor of 1. So, if we move towards the left, then the next bit is equal to 1. So, this one gets multiplied by the factor of 2. Then the next bit is equal to 0. And it will get multiplied by the factor of 4. Then after, the next bit is equal to 1. So, it will get multiplied by the factor of 8. And likewise, as we move towards the left, then the weight of each bit will increase by the factor of 2. And the decimal equivalent of the given binary number is the summation of all these products. That is equal to 128 plus 64 plus 32 plus 0 plus 8 plus 0 plus 2 plus 0, which is equal to 234. So, in this way, we can convert any binary number into the decimal equivalent number. Alright, so now let's take one more example. So here, similar to the decimal number system, before this binary point, as we move towards the left, then the weightage of each bit will increase by the factor of 2. While, after this binary point, the weightage of each bit will reduce by a factor of 2. So, before this binary point, the number is 101. That means this 1 will get multiplied by the factor of 1. While the next bit will get multiplied by the factor of 2. And if we see the next bit, then it will get multiplied by the factor of 4. And therefore, their summation is equal to 4 plus 0 plus 1. That is equal to 5. Similarly, if we consider the number just after this binary point, then it is equal to 011. So, here this 0 will get divided by the factor of 2, while the next bit 1 will get divided by the factor of 4. And likewise, this 1 will get divided by the factor of 8. So, if we see the summation, then it is equal to 0 plus 0.25 plus 0.125. That is equal to 0.375. That means for the given binary number, if we see the decimal equivalent number, then is the summation of all these terms. That is equal to 5 plus 0.375, which is equal to 5.375. Similarly, you can pause the video, and you can convert this given binary number into the decimal equivalent. So, if you try to convert into the decimal equivalent, then this is the weightage of each bit. So, from the binary point, as we move towards the left, then the weightage of each bit will increase by the factor of 2. And after the binary point, the weightage of each bit will reduce by a factor of 2. So, if you take the summation of all these products, then it is equal to 8 plus 4 plus 0 plus 1 plus 0.5 plus 0.25. That is equal to 13.75. So, in this way, we can convert any binary number into the decimal equivalent. So, in the next video, we will see that how to convert any decimal number into the binary equivalent number. So, if you have any questions or suggestions, then do let me know here in the comments section below. If you like this video, hit the like button and subscribe to the channel for more such videos.